The rain stopped an hour ago and the street is still moving. People are moving through the streets, stepping around the edges of the larger puddles, adjusting their routes along the pavement to avoid the sections where the water runs deepest. The streets are moving with water. It runs along the gutters in a continuous brown current, carrying with it the accumulated contents of the morning. Kitchen waste tipped from back doors, ash from hearths swept into the channel, the runoff from the yards and the courts and the narrow passages between the buildings that connect the front street to the back alleys behind it. The water finds the lowest line through the street's surface and follows it, picking up everything that sits in that line and carrying it toward the drain at the corner where it disappears, or appears to disappear. The drain at the corner of a Victorian street in the middle decades of the 19th century is not a solution. It is a transition point, the place where the problem moves from visible to invisible, from the surface of the city to something beneath it, from a condition that can be seen and stepped around to a condition that is handled by systems that the people stepping around it will never directly observe. The water goes into the drain. What happens to it after that is, for most of the people on this street, entirely unknown and entirely unimportant as long as it keeps going. The city above this street is a functioning city. It is busy in the way that a Victorian industrial city is busy, with movement, with commerce, with the ordinary transactions of working life conducted at a pace that the industrial period has accelerated beyond anything the previous century would have recognized. Factories are running, markets are open, carts are moving through the wider streets, carrying goods between the places that produce them and the places that consume them. The surface of the city operates with a visible energy and a visible order that suggests a system under control. Beneath the surface, the situation is different. Population growth has done something to the city that the city was not originally built to handle. In the early decades of the 19th century, the population of England's major industrial cities expanded at rates that had no precedent in the country's history. People arrived from rural areas, from Ireland, from smaller towns, drawn by the wages and the work that industrial production made available. They arrived faster than housing could be built to receive them and faster than the existing infrastructure of the city could be extended to serve them. The streets that had drained adequately when they served a smaller population were now carrying the output of a population many times larger through channels built for a fraction of that load. The older habits of waste disposal, the cesspit beneath the yard, the channel running down the centre of the street, the practice of emptying household waste into the nearest available watercourse, had functioned tolerably in a smaller and less densely populated city. In the industrial city of the 1840s, they were failing visibly and dangerously. The cesspits were full and overflowing into the soil around them. The street channels were carrying volumes they were not designed for. The rivers and streams that ran through the city's geography were receiving the combined waste of hundreds of thousands of people, and were no longer rivers in any meaningful sense of the word. The city had to build a second city beneath itself. Not a dramatic or sudden decision. The construction of Victorian sewer networks happened over decades, through arguments between engineers and municipal authorities and ratepayers about cost and responsibility and technical approach. But the underlying logic was simple, and it was eventually inescapable. The city above could not continue to function if the city below remained unbuilt. The sewer was not a public amenity in the sense that a park or a market hall was a public amenity. It was the hidden machine that made the visible city possible. If you haven't already, like and subscribe to the archive and leave a comment below. It helps more than you might think. Settle in. We are going underground shortly, and it is worth understanding what we are descending into before we go. Walk along the street slowly and look at what the surface tells you. The pavement, where it exists, and in many working districts the pavement is intermittent, broken, partially replaced with compacted earth, where the original stone has been removed or has simply subsided into the soft ground beneath, carries the marks of continuous water movement. The stone is worn smooth along the lines where runoff regularly flows, polished by the passage of water in the same way that riverbed stone is polished, which tells you something about the volume and the regularity of what passes over it. The channels cut into the edges of the road surface where the street meets the building line are deeper and wider in some sections than in others, reflecting the variations in gradient and in the volume of water that particular section of street regularly carries. Rain does not clean this street. This is the first thing to understand clearly. Rain adds to what the street is already carrying. It takes the dry deposits of the intervals between rain events, the ash and the coal dust and the animal waste and the kitchen refuse and the workshop sweepings that have accumulated on the street surface and in the gutters since the last rain, and it mobilizes them. It picks them up and moves them. It concentrates them in the lowest parts of the street's drainage pattern, and it pushes them toward the available outlets. The rain does not remove these materials from the city. It redistributes them to wherever the drainage system directs them, which in a poorly drained district may be simply to a lower section of the same street, or to the yard of a building whose drain inlet sits at the receiving end of the street's gradient. The people who live and work on this street have developed a practical knowledge of its drainage behavior that is never written down and never formally taught. They know which sections of the pavement hold water after rain and for how long. They know which corner produces the worst overflow when the drain at the bottom of the slope becomes blocked, which happens regularly enough to be a predictable event rather than an unusual one. They know the particular smell that rises from the gutter in warm weather after the street has been dry for several days, which is the smell of what has been deposited in the channel and left to settle in the heat. They step around these things not because they find them remarkable, but because avoiding them is part of moving through the street, in the same way that avoiding a low door frame is part of moving through a building. A routine physical adjustment that has been performed so many times, it requires no conscious decision. The drain at the end of the street is a point of disappearance. It takes what the street produces and removes it from the visible surface of the city. In a properly functioning Victorian sewer network, it connects to a tunnel that carries the material away from the district entirely through a system of increasing channel sizes toward a final outfall somewhere downstream of the populated areas. In a district where the sewer network has not yet been extended, or where the existing drainage is old and inadequate, the drain connects to something less orderly. A culverted stream, an old brick-lined channel of uncertain destination, a cesspit that was built for a smaller population and has long since exceeded its designed capacity. The city's cleanliness, such as it is, depends on this consistent act of pushing filth out of sight. Not eliminating it, the material does not cease to exist when it passes into the drain. It continues to exist somewhere, doing whatever it does in whatever system receives it. But the act of making it invisible is itself a form of civic order, and the Victorian city invests considerable engineering effort and municipal expenditure in maintaining and extending the infrastructure that allows this invisibility to be sustained. The street above teaches you where not to stand, where not to breathe deeply, what to step around, what to ignore. The system below is built on the same principle, applied at a larger and more deliberate scale. The city functions by maintaining the fiction of its own cleanliness, and the sewers are the infrastructure that fiction requires. The access point is a cast iron cover set into the pavement, its surface worn flush with the surrounding stone by the passage of feet and wheels over many years. A sewer worker lifts it with a hook, a practiced motion, economical, requiring no particular effort from someone who has done it hundreds of times, and sets it aside against the curb. The opening below is dark, and the air that comes up from it is immediately noticeable. A different quality of air from the street above, even on a street whose air is not particularly clean. It is warmer than the street air slightly and damper, and it carries a particular combination of smells that is recognizable once encountered and not easily forgotten. The worker does not react to it. It is the air of his workplace, as familiar to him as the particular smell of a mill floor is familiar to a mill operative, or the particular smell of a foundry is familiar to a foundry worker. He descends by iron rungs set into the brickwork of the shaft. The descent is perhaps 12 to 15 feet in a typical Victorian sewer access shaft, though this varies considerably depending on the depth of the tunnel and the age of the construction. The shaft is narrow, wide enough to allow a man to descend with his equipment, but not wide enough to allow him to turn around easily once he is inside it. The lamp goes down first, attached to his belt or carried in his teeth or lowered ahead of him on a line, depending on the individual worker's preference and the particular requirements of the descent. The tools, the rod, the scraper, the bucket on a rope, follow in whatever configuration the work of the day requires. At the bottom of the shaft, the world changes in a way that is immediate and complete. The street above is a surface world, open to the sky, subject to weather, populated with movement and sound and the ordinary visual complexity of an urban environment in operation. The tunnel below is none of those things. The sky does not exist here. Weather does not reach here in any direct sense, though the consequences of weather above, the increased flow after heavy rain, the debris that enters through the street drains during a storm, are very much present in the tunnel's behavior. The visual field contracts to what the lamp illuminates, which is a curved brick arch above, a brick channel below, carrying a continuous flow of dark water, and brick walls on either side that curve toward each other in the particular geometry of the egg-shaped Victorian sewer profile, designed to maintain flow velocity at varying water depths. The worker moves carefully. The footing is uncertain in a way that requires continuous attention. The invert, the curved lower surface of the tunnel where the flow runs, is wet and in some sections carries a deposit of settled material that makes the surface slippery in a way that dry brick would not be. The worker knows this and adjusts his movement accordingly, placing each foot with a deliberateness that someone moving through a familiar above-ground environment would not need to employ. A fall in a sewer tunnel is not a trivial event. The tunnel is not equipped with the informal safety resources that an above-ground environment provide. No passerby to help, no easy way to signal distress, no quick route to the surface if something goes wrong. The system feels less like a public improvement from inside it than it does on the engineer's drawing or in the municipal committee's report. From inside, it feels like what it is, a buried obligation, a necessary infrastructure operating in conditions that the people whose waste fills it will never experience directly, maintained by labor that the city requires and rarely discusses. Run your hand along the tunnel wall and feel what Victorian engineering actually is at its most fundamental level. Brick. Fired clay pressed into a standard form and laid in courses by workers who spent their days underground, in conditions not substantially more comfortable than those of the maintenance workers who came after them. The brickwork of a Victorian sewer tunnel is not decorative. It does not aspire to the architectural ambition of the civic buildings above ground that were also built from brick in this period. It is purely functional in its intentions, and the function it serves is precise and demanding in ways that purely functional structures often are. The shape of the tunnel is not arbitrary. The egg-shaped cross-section, wider at the base, narrowing toward the crown, was developed through engineering calculation and practical experience as the profile best suited to maintaining continuous flow through a tunnel that carries varying volumes of water at varying times. When the tunnel is running at low volume, as it does for most of each day, the flow concentrates in the narrower lower section of the profile, maintaining enough velocity to carry suspended solids along rather than allowing them to settle on the invert. When the tunnel is running at high volume after heavy rain, the wider upper section accommodates the increased flow without the tunnel backing up into the street drains above. Every curve in the tunnel serves a purpose. Bends are calculated to maintain flow rather than interrupt it. Too sharp a curve creates turbulence and encourages deposition at the outer edge of the bend. Gradients are measured and maintained within specific tolerances because the flow depends on gravity, and gravity depends on the consistent fall of the tunnel's invert from the higher parts of the catchment area toward the lower. Junctions where tributary tunnels connect to main tunnels are designed so that the incoming flow joins the main flow without creating a dead zone, an area of reduced velocity where material would settle and accumulate. The inspection chambers, the wider sections of tunnel at regular intervals where the workers can stand upright and turn around and assess the condition of the flow in both directions, are not architectural features. They are operational requirements, the underground equivalent of the maintenance access points that any complex mechanical system requires at intervals along its length. Victorian order is expressed here in masonry rather than in legislation or in factory discipline. The tunnel does not ask the water and the waste that flows through it to behave in a particular way. It is built in such a way that the water and the waste have no option but to behave in the required way, because the geometry of the space leaves them no alternative. The direction is predetermined, the velocity is managed, the deposition is minimized by design. The system disciplines filth through the application of engineering rather than through authority, and the discipline is more reliable for being physical rather than social. The sewer does not stop filth. It contains the filth, directs it, and removes it from the spaces where its presence would make ordinary life impossible. It is the underground expression of the same Victorian impulse that produced the factory's drive shafts and the railway's timetables, the conversion of chaotic natural processes into controlled, directed, predictable systems. By the middle of the 19th century, the men who work in the sewer network have developed a professional identity and a practical knowledge base that has no formal institutional recognition and no established career structure, but that is nonetheless real and specific and distinct from the knowledge required for any other kind of work. They are called flushers, or sewer men, or in some districts simply the underground men, and they move through the tunnel network with a familiarity that is the product of years of accumulated experience in the specific tunnels of a specific district, knowledge of which sections run slow in dry weather and require more frequent clearing, which junctions are prone to blockage from a particular kind of debris, which sections of tunnel have brickwork that is beginning to deteriorate and requires monitoring, which access shafts have rungs that are loose and which have drainage problems at the base of the shaft that make the descent more difficult than it should be. Their tools are specific and well understood. The lamp is the most essential. Without light, the tunnel is unusable and the safety risk is absolute. The lamp they carry is designed to function in a confined and potentially gas-rich atmosphere, which is a real concern in sewer tunnels where organic decomposition produces gases that can accumulate in pockets and that represent a genuine danger if a conventional open flame is introduced into them carelessly. The rod is used to probe ahead and to clear partial blockages before they become complete ones. The scraper clears the deposits that accumulate on the invert despite the designed flow velocity. The heavier materials that settle out even in a well-functioning tunnel during periods of low flow. The bucket and rope carry the cleared material up to the surface in manageable loads. The work is not dramatic in its daily reality. It is repetitive, wet, dark, and physically demanding in the particular way that confined space work is physically demanding. Not the gross physical exertion of heavy labor above ground, But the sustained low-level effort of moving carefully through tight spaces for extended periods, maintaining concentration in an environment where the consequences of a lapse in attention are more serious than they would be in a more forgiving workplace. These men do not produce anything. This is worth stating clearly because the Victorian economy's framework for understanding the value of labor is largely organized around production. The making of goods, the movement of goods, the selling of goods. The sewer worker makes nothing and moves nothing that has commercial value. What he does is prevent the collapse of the conditions that make commercial production possible. He removes the accumulated consequences of the city's operations from the channels that carry them, maintaining the flow capacity that keeps the underground system functioning, which keeps the street surfaces manageable, which keeps the population above them in the condition of health and mobility that allows them to continue working. His labor is invisible in the most literal sense. It happens underground, in the dark, in spaces that the population whose waste he manages will never see. The street above him on a working morning looks exactly the same whether he is in the tunnel beneath it or not. The invisibility of the work is structural. It is built into the design of the system, which is designed specifically to make its own operation unobtrusive to the people it serves. Respectable Victorian society does not discuss this work in the same terms that it discusses mill work or railway construction or the building trades. It is too close to what it manages to be discussed comfortably. The men who do it are employed regularly and necessarily by the same municipal authorities that maintain the fiction of the clean Victorian street above. Their presence proves that even the most automated-seeming infrastructure still depends, at its operational core, on human bodies moving through difficult conditions with specific knowledge and practical tools. Stand at a street drain during heavy rain and watch what enters it. The water arrives from multiple directions simultaneously. It comes off the rooftops through the down pipes that discharge at pavement level, carrying the accumulated deposit from the roof surfaces, soot, dust, organic material, in suspension. It comes along the gutters from both directions, converging at the drain inlet from the full drainage catchment of the street. It comes through the gaps in the pavement where the surface is broken or uneven, having collected in the hollows and now finding the drain as the lowest available outlet. It comes, in heavy rain, directly from the sky in quantities that exceed what the gutters and channels can carry in an orderly way, producing a sheet flow across the pavement surface that carries whatever is on that surface toward the nearest drain. All of this enters the underground system simultaneously. Below the drain inlet, the tunnel receives the combined input of every drain in its catchment area at the same moment. The flow that the tunnel carries in dry weather, the household waste and the workshop runoff, and the ordinary drainage of the district's daily operations is joined during heavy rain by a volume of surface water that can multiply the tunnel's load many times over within a short period. The engineering of the tunnel has accounted for this, within limits, through the sizing of the main tunnel and the calculation of the gradients. But the limits are real, and the engineering has limits. Maintenance workers monitor conditions during and after heavy rain events because heavy rain is when the system's vulnerabilities become apparent. The sections of tunnel where the gradient is slightly insufficient reveal themselves when the increased flow carries more suspended material than the velocity can keep in suspension. The material settles and the invert begins to build up a deposit that will restrict the flow further if it is not cleared promptly. The junctions where tributary tunnels connect to main tunnels reveal themselves under high flow conditions as potential points of surcharge. Situations where the main tunnel is running too full to accept the tributary flow cleanly, creating a backing up effect in the tributary that can eventually push back through the street drains above. The sections of tunnel where the brickwork is deteriorating reveal themselves under the increased hydraulic pressure of a storm event in ways that routine inspection under normal flow conditions might not detect. The rain tests the system's true capacity rather than its designed capacity, and the gap between those two things, which exists in every engineered system and is managed rather than eliminated, becomes briefly visible during and after significant rain events before the system returns to its ordinary operating condition, and the gap closes again. The section of the city above continues operating through all of this. People move through the rainy streets. Businesses remain open. The ordinary life of the district proceeds on the surface, while the underground system below manages its storm event in the dark, without the people above it being aware of the specific pressure that the rain is placing on the infrastructure beneath their feet. Quiet pressure building. The system is temporarily stressed and temporarily visible to the men inside it. The street above is, as always, unaware. The underground city has its own geography, and that geography is expressed not in street names and building numbers but in gradients, invert levels, catchment boundaries, and outfall locations. An engineer surveying a Victorian sewer district works from measurements that the surface city does not require. He needs to know the precise fall of the ground across his survey area, not approximately, not to the nearest foot, but to within fractions of an inch across distances of hundreds of yards, because the difference between a tunnel invert that falls at the correct gradient and one that falls at a slightly incorrect gradient is the difference between a tunnel that maintains self-cleansing velocity and one that silts up with deposited material and requires constant manual clearing to remain operational. The survey produces drawings that look nothing like the maps of the surface city, where a street map shows addresses, building lines, property boundaries, and the named routes through the urban fabric. The sewer survey map shows contour information, flow directions, tunnel profiles, junction angles, chamber locations, and the relationship between the underground network and the surface topography that determines where gravity will and will not assist the movement of waste. The two maps of the same area, the surface map and the underground map, are describing the same physical space from entirely different operational perspectives, and the relationship between them is not always straightforward. A street that runs along the natural ridge of the underlying topography may be the most direct route between 2 points on the surface, but the worst possible route for a sewer because the gradient away from the ridge runs in both directions, and a tunnel following the street line would have to choose one direction of fall and leave the other side of the ridge without adequate drainage. A street that drops steeply toward the river may be difficult and dangerous to walk along in icy weather, but ideal for a sewer because the gradient provides exactly the fall rate that the engineering requires without any need for mechanical assistance. The calculation of the tunnel system involves the Victorian bureaucratic mind at its most particular and most thorough. Every section of tunnel must be sized for the catchment area it serves, taking account of the population density, the nature of the land use, residential, commercial, industrial, and the rainfall characteristics of the district. Every junction must be checked for hydraulic compatibility, the tributary flow joining the main flow at an angle and velocity that will not create turbulence or backflow. Every outfall must be located and sized so that the final discharge of the collected waste enters the receiving watercourse or treatment works at a rate and in a manner that the receiving system can handle. The paper plans that result from this calculation process are precise documents that translate the physical reality of the underground city into an administrative form that can be checked, approved, contracted, built, and inspected. They sit in the municipal engineer's office, periodically updated as the network is extended or repaired, constituting an archive of the invisible infrastructure that the visible city depends upon. The city above has streets and addresses. The city below has slopes, chambers, and routes. Both are real. Only one of them appears on the maps that most people ever look at. Not all of the city sits on ground that slopes conveniently toward the outfall. In the flat sections of an industrial city, the areas near the river, the low-lying districts that developed on ground with insufficient natural fall to provide sewer gradients by gravity alone, the waste that enters the underground system cannot be moved by the passive force of the slope because the slope is insufficient or absent. It accumulates in low points of the network and it stays there unless something actively moves it. The mechanism that actively moves it is the pumping station. The pumping station is the muscular component of the sewer system, the place where the passive hydraulics of the tunnel network meet the active mechanical force of steam-powered machinery, and where the waste that gravity cannot shift is lifted and redirected into sections of the network where the gradient can take over again. Enter a Victorian pumping station, and the character of the underground system changes entirely. The tunnel world is brick, water, darkness, and the sound of flow. The pumping station is ironwork, steam, pistons, valves, and the particular combination of mechanical sounds that steam-driven machinery produces. The rhythmic stroke of the pump mechanism, the hiss of steam through the valve gear, the low vibration that the machinery sends through the floor and the walls of the building. The men who work here are not tunnel men, they are engine men, with a knowledge set closer to that of a mill engine operator than to that of a sewer flusher, though they share with the tunnel workers the condition of performing essential and continuous labor in a place that the public neither visits nor thinks about. The pumps lift sewage from the low collection sumps where it has accumulated and force it upward through rising mains, pipes under pressure rather than open channel tunnels, to a level from which gravity can once again take over and carry it the rest of the way to the outfall. The machinery that does this is substantial. The forces involved, the weight of the fluid column being lifted, the pressure required to move it through the rising main against that weight, demand engine power of a scale comparable to what a small mill would require for its production machinery. The damp floors of the pumping station carry a particular smell that combines the mechanical environment of the engine room with the sewer environment of what the engine is processing, which is an atmospheric combination found nowhere else. The workers who spend their shifts in these buildings develop the same habituated indifference to the conditions that characterizes the workers in every other part of the underground system. Not because the conditions are comfortable, but because habituation is the body's practical response to a working environment that cannot be changed. The sewer becomes part machine, part river, part bureaucracy. The city's survival depends on hidden engines doing ugly work politely in buildings that are often architecturally substantial on the outside. The Victorians built their pumping stations with a civic seriousness that acknowledges the importance of the function even while the function itself remains unmentioned in polite company, and entirely functional and unglamorous on the inside. Come back up to the surface. The access cover goes back into place with the same practiced motion that removed it. The hook, the lift, the set down into the frame, the slight adjustment until the fit is flush with the surrounding pavement. Within 30 seconds of the cover being replaced, the access point is invisible. There is no mark on the surface of the street to indicate that a worker descended into a tunnel here this morning, that the tunnel beneath is currently carrying the waste of several thousand households through the darkness below this pavement toward an outfall several miles distant, that a network of brick tunnels of varying sizes occupies the ground beneath every street in this district to a depth that varies between 8 and 30 feet depending on the local topography and the age of the construction. The street looks clean. The Victorian street is not a clean surface in any absolute sense, and a close examination of its pavement and gutters would quickly confirm this. But it looks managed. The waste that it produces is being handled. The drainage is functioning. The flows are moving. The underground system is doing what it was built to do, and the surface of the city presents the appearance of an urban environment that has the situation under control. Respectability in the Victorian city depends significantly on this appearance of control, and the appearance of control depends significantly on concealment. The cleaner Victorian street of the mid-19th century compared to the early decades of the century is not a street from which filth has been eliminated. It is a street from which filth has been assigned a route, downward into the underground system, away from the visible surface and into the infrastructure that was built specifically to receive it. The filth continues to exist. It continues to move through the city's geography. It continues to be managed and processed and eventually discharged somewhere. But it does so in a space that is not the street, and the street benefits from its absence in a way that does not require the street's inhabitants to understand or acknowledge the system that produced the benefit. People walk above systems they do not understand and in most cases do not think about. The worker crossing this pavement on her way to the market has no reason to consider the tunnel beneath her feet. The shopkeeper opening his premises has no reason to think about the gradient of the sewer invert below his shop floor or the capacity of the junction chamber 2 streets away that handles the combined flow from this district. The children running along the pavement have no concept of the maintenance worker who was in the tunnel below this section of street 3 days ago, clearing a partial blockage that, had it been left unattended for another week, would have caused a backing up event significant enough to affect the street drains at the top end of this block. The hidden labour continues while public life proceeds above it. The civilization operates by obscuring the work that keeps it operational, by building that work into spaces where it cannot be seen, performed by workers whose presence is required and whose labour is essential and whose workplace is, by design, invisible to the people who benefit from it most directly. Victorian England did not become more orderly by becoming more honest about what order requires. It became more orderly by becoming better at hiding what order requires, underground, in the dark, behind cast iron covers set flush with the pavement. The workers have left for the night, and the tunnel continues without them. This is the condition that the engineering was designed to produce. A system capable of operating continuously without requiring continuous human presence. The tunnel does not need someone in it to carry the flow. The brickwork holds its shape without inspection. The gradient maintains the velocity without adjustment. The junctions pass the flow from tributary to main channel without direction. The overnight hours are the system's demonstration of its own designed autonomy, and the demonstration runs successfully every night across the full extent of the network. Water enters the system through the street drains above. It travels through the network by gravity, following the calculated fall of the invert from the higher catchment areas toward the lower. At the flat sections it accumulates in the sumps until the pumping station machinery, which runs continuously, tended by overnight shift workers whose presence in the pumping station constitutes the system's only required human component during these hours, lifts it into the rising mains and sends it on toward the outfall. The outfall discharges continuously into the receiving watercourse, which carries it further away from the city. The city grows because the underground network grows with it. This is the relationship that the Victorian period established and that every subsequent period of urban development has inherited. A city can expand its populated area only as far as its underground infrastructure can be extended to serve the new areas. The sewer network is not a response to urban growth, or rather, it begins as a response to urban growth, but quickly becomes a precondition of further urban growth because new development without sewer connection is development that the municipal authority cannot permit and that the population cannot safely inhabit. The underground infrastructure sets the pace of the surface expansion. Victorian cities did not become modern by becoming clean. This is the simple truth that the underground system makes visible if you spend enough time below the surface to understand what is happening there. They became modern by building systems powerful enough to carry the dirt away, not to eliminate the dirt, The dirt continues to be produced in the same quantities and of the same character regardless of whether the sewer system exists or not. But to carry it away from the spaces where people live and work and move through, to process it through the underground network, to deposit it at a sufficient distance from the populated areas that its presence does not interfere with the functioning of the city above. The tunnel beneath this street will be here long after the shift ends and the access cover closes and the street returns to its ordinary surface life. It will carry the city's waste through the night and through the following day and through every subsequent day, for as long as the city above it continues to produce waste, which is to say for as long as the city above it continues to exist. The brickwork will require maintenance. The gradients will require monitoring. The junctions will require periodic clearing. The pumping station machinery will require servicing and eventually replacement. But the system itself, the physical fact of the underground network threading through the ground beneath the streets, is a permanent condition of the city's geography now, as much a part of the city's infrastructure as the streets above it. The final image of this moment in history is simple, and it needs no elaboration. A brick tunnel, curved and dark, carrying water into the distance until the lamplight fails and the darkness takes over, and the sound of the flow continues beyond the point where anything can be seen. The city above is quiet. The system below is running. The work that keeps the visible city possible continues in the only way that such work can continue. Invisibly, underground, without acknowledgement and without pause. The cover has been replaced and the street has closed over the tunnel again. You remain for a moment at the pavement's edge, the distant sound of water movement somewhere below your feet. The gaslit street continuing its ordinary business above it, neither surface aware of the other. The city rests on what it removes, and what it removes never stops moving. These are the systems that kept the visible city possible, built in the dark, maintained in the dark, and designed to remain there permanently. If you'd like to return, the archive is here.